Gravitational lensing is one of the most powerful tools that astronomers have at their fingertips, and yet it's a natural telescope that nature has delivered to us. The gravitational power of an entire galaxy or a galaxy cluster or a star that focuses the light from a more distant object, magnifying it by thousands of times in a way that we just couldn't produce a telescope big enough here on Earth, and yet we can take advantage of this. And there's some really classic examples of gravitational lenses out there. Einstein crosses, places where you can see multiple other galaxies lensed many times around a foreground object. But one of the more interesting things is gravitationally lensed quasars. This is where you've got a quasar, an actively feeding supermassive black hole that is gorging on material, firing out these intense beams of radiation. And it's different from a quieter black hole like what we have here at the heart of the Milky Way. Now, my guest today is Dr. Matt O'Dowd, and you might recognize him. He is the host of the PBS Spacetime channel, which is one of the best astronomy, astrophysics, quantum mechanics explainers out there on YouTube. But he's also an astrophysicist in real life. He's an astrophysicist at Lehman College of the City University of New York, and he and his team are working on a proposal to use Vera Rubin to detect gravitational lensing events where you could get better resolution of a quasar as being lensed by a foreground galaxy. And so I saw his name on the paper and I just had to talk to him about this. So enjoy this interview with Matt O'Dowd. Matt, it's good to see you again. I think last time we chatted, you were stuck in your apartment during the epidemic.
That's right. Good to see you too, Fraser.
Yeah, now it wasn't much of a difference for me. I live in the forest. I work from home, but for you in the middle of one of the most populous cities on Earth, I'm sure it was a tough time.
They were crazy times, yeah. In the heart of New York City, it was a strange place at that time. But as you can see behind me, I now live in the forest. So,
perfect. Yeah. I highly recommend this lifestyle. Cool. So now I go through the archive every day, which is a place of sort of pre-press location that astronomers post all of their research. And I am sort of looking for the kinds of stories that I think are going to interest my audience. And one caught my eye, and I'll give the title, Resolving the Vicinity of Supermassive Black Holes with Gravitational Microlensing. And that all sounded great. And then I looked at sort of the plan, which is to use Vera Rubin, and then I'm all in. And then I wanted to sort of figure out who should I reach out to and see if I can do an interview. And I saw your name in the list, which was great. So, not only are you a science communicator with your incredible PBS Spacetime channel, but you are actually a scientist.
Well, I try, yeah. On my good days, I sometimes get to think a little bit about the universe myself.
So explain the plan. What are you guys proposing?
So this is something that a number of us have been thinking about for some time now. My PhD advisor, who's Rachel Webster at Melbourne University, is one of the OG quasar people and has been trying to do this for a long time. And there's been this small group who've been pushing at what is an extremely difficult but ultimately mind-blowing, just holy grail of an experiment if we can do it. And it would have such impact that all these years we haven't stopped thinking about it, but it's been so hard. So the idea is that first we have quasars, right? So the largest black holes in the entire universe, okay, these things that have grown in the hearts of galaxies since the beginning of time, occasionally feeding on material that gets pumped down to the centers, waking up as they turn that material into pure energy, blasting it out across the universe. We see these things twinkling all across the boundaries of the universe. And so awesome things in themselves. And they teach us how black holes grow and how black holes influence the evolution of the universe, etc. Very difficult to study because comparatively they're tiny. They're a speck in the center of the galaxy, and there is no telescope we could possibly build that could resolve that speck. So they remain specks of light. And so a lot of people have tried for a long time to figure out how to get in there and see what's happening around the black hole. I'm sure all of your viewers have seen the picture of the Event Horizon Telescope, the two black holes, imaged with one of them being our own Milky Way Sagittarius A star. Those are the only two we can do that for.
Right. And
all
they're
the
not
rest
quasars.
of them are beyond our reach. Exactly, yeah. But there are ways to do it. And one of the ways, well, there are really two ways. And the way that this paper gets to is that in very rare cases, a distant quasar might be by great good chance be aligned directly behind some very massive object, typically a galaxy. And as we know from Einstein's general relativity, mass bends the fabric of space. And so in these cases, we have light from the quasar, which would normally be going in different directions, gets bent back around by the galaxy as though it were a lens towards us. And so we end up seeing multiple images of the same quasar, 2, maybe 4 images surrounding that galaxy. And we also see that those images are fluctuating because that galaxy is made up of stars. So it's not a very good lens. So gravitational lens is what we call these things. This is gravitational lensing, but it's not a very good lens. We wouldn't build this in a lab. It's made up of individual stars. Everything's moving. The individual gravitational fields cause everything to fluctuate, which sounds bad, except it allows us to do this experiment. So as well as the whole galaxy creating this incredibly beautiful effect, the individual stars actually have their own magnification effect that sweeps across the inner structure of the quasar. So you've got these extremely high magnification bands, say, that sort of do these sort of radar maps across the inner structure. And what that looks like to us when we just look at these, say 4 images of quasar, is that they sort of twinkle independently of each other. But then if we're able to break apart the light, take a spectrum of the light, or even just, look at the light in different chunks, we can see that different parts of that spectrum vary in different ways. And those different parts of the spectrum correspond to different regions inside the quasar. And so it becomes possible to actually do a type of mapping of the inner structure by just watching how the gravitational fields of these stars pass across the inner quasar. And this particular, so we've been playing around with this, and we've got some quite interesting results and measurements about quasars. But the holy grail that I'm talking about is when you get this super high magnification band called a caustic, as you know because you read the paper, it sweeps across the black hole itself. And then you get this, what we think is going to be a very distinct signature, where you see the brightness rise and rise and rise as the high magnification region passes closer and closer to the brighter parts near the black hole. And by the way, the black hole in these quasars is surrounded by a disk of material. If you're familiar with the interstellar black hole, there's this disk of material pouring into the black hole. This is the accretion disk. It gets brighter and brighter as you get closer to the black hole. So as that magnification band gets close to the center, you've got this rise in brightness. But then near the black hole itself, so the black hole is black, no light can escape it. And even surrounding the black hole, there's this shadow. There's this region where matter can't exist because the warping of space-time is so strong that everything just spirals straight into the black hole. So we expect this substantial shadow around the black hole. And in fact, that's what you see in the Event Horizon Telescope. That dark circle is this black hole shadow. So when our band gets to that dark region, we see the brightness go up, and then in perfect circumstances, it can dip down and then go up again. In less perfect circumstances, it sort of does these sort of other different shapes. And by measuring that dip, we are, in a real sense, measuring the black holes, of these quasars that can be many billions of light years away. That's the long story.
That's the hope,
I guess.
So I want to just sort of see if I understand this correctly, that, in addition, like normally with a strong gravitational lens, you've got this, say, galaxy cluster that's in the foreground, and you've got this lensed galaxy that's in the background, and the galaxy is containing this supermassive black hole that is actively feeding. This is your quasar. And you're getting, and we're very familiar, and I'm sure our editor will show a bunch of cool pictures of Einstein crosses and various gravitational lenses where you can see these multiple versions of a quasar. But you're saying that in addition to just the overall gravitational lensing of the galaxy cluster itself, you're getting tiny versions of this from all the constituent elements of the galaxy cluster, the stars, the dwarf galaxies, the globular clusters, all the bits and pieces, and that they're going to create this texture that is on top of this overall gravitational lens that you're
Exactly
seeing.
right.
The trick is that you just need to be able to...
Text is a nice word for it.
To see it and map it. And it gives you higher resolution in the object that you're seeing. Because I know without knowing the shape of the lens itself, you really can't reconstruct the shape of what is being lensed.
That is less true than you would imagine. It's incredible what you can reconstruct with gravitational lensing, especially so in the era of machine learning, it becomes possible to, with some constraints. So in the case of these quasars, by the way, the lens is typically a single galaxy, which makes it a lot easier than a cluster of galaxies. And with a single galaxy, you can make some general assumptions about, stuff we know about galaxies and their smoothness. And you can really go a long way to reconstructing what look like otherwise hopelessly scrambled things. The old trope of the agent saying, enhance this picture, and then it becomes ridiculously perfectly resolved. Well, it feels a bit like that sometimes. These quasars, though, you can't really resolve them directly. They remain point-like. But the way we get that new resolution is when we essentially add a new dimension. The dimension is wavelength, the wavelength of light. So when we break up the light into a spectrum and we can see that the ultraviolet light, we know that must be coming from close to the black hole because that's energetic light. The infrared light must be coming from further away, must be larger. And then you get various wavelengths of light from particular elements that we know must be in there, oxygen and hydrogen, all this stuff. And so when we see this stuff fluctuate in different ways as our kind of magnification sweeps across, then we can start to build up this picture of where these things are in the quasar. So we end up not having an actual photograph, but we gain more and more evidence. Every time we do this, we gain more and more evidence for our kind of theoretical picture of what the quasar looks like.
And so why are you suggesting that Vera Rubin is the key to being able to make these observations? What does Vera Rubin bring to the table that no other telescope has so far?
The reason this experiment has been so difficult so far is two things. Number one, there aren't that many what we call strongly lensed quasars. We've been dealing with the same 100-ish for a long time. And so that's number one. Number two is that, related to that is the fact that these events, like when this caustic curve crosses the supermassive black hole, are super rare. Maybe you'll show the Einstein cross. In this case, it's expected to happen once every couple of years. But for almost every other one of these lensed quasars, they happen once every 20 years, right? So it takes a long time. Also, you don't know when it's going to happen, okay? So number two is just, so the rarity of the event is number one, and that's contributed to by the rarity of these lensed quasars. And number two is just the resources needed to see the event happening. We don't have any way to predict long in advance when it'll happen, so we have to monitor. We have to have telescopes pointing at these things, all the time. Okay, so for something like the Einstein cross, you kind of want to watch it every couple of days. For something for the others, every week or so. But that's an enormous amount of telescope time, and there are plenty of astronomers who don't care about this, who want to use the telescopes for other things. But the Vera Rubin and the Legacy Survey of Space and Time, LSST survey, will monitor the entire southern sky for 10 years with, looking at every point roughly every 3 days. And so essentially we get that monitoring that we've been trying to do now for a couple of decades, in fits and starts. We get it for half the sky for free. And because this survey is going to be so deep and comprehensive, we expect to discover thousands more of these strongly lensed quasars. So many, in fact, that we expect to see a couple of these, what I'm going to now call caustic crossing events, potentially a couple every year. And we'll get the monitoring for free. And so then if we sort of get our kind of pipeline together and are ready to do it and know how to spot one of these rising events, we can then turn on other telescopes. So this becomes super valuable when you swivel your radio telescope and your X-ray telescope and all of this stuff.
So I mean, in addition to Vera Rubin finding, like, it will find you thousands of more potential targets. So you're going to be looking at the entire sky, and you're going to be looking for that telltale sign in any of them that are happening that you're starting to move towards this brightening. And then you can shift some other observatory to point at it and confirm that, yes, the brightening is indeed happening. How much notice do you think that you're going to get from when you see, you detect one of these to the ideal time to observe it with a really powerful telescope?
It's a question that we are currently trying to answer, because these, we're trying to figure out what a totally random galaxy of stars is likely to do to the quasar. So we don't know where the stars are in that galaxy. We roughly know, their density, how many stars there are in that region of the quasar. We don't really know where they are and what the whole system really looks like. And so it's sort of a bit probabilistic. So what we're trying to do now is develop methods to, once we see that rise, to first say, this is definitely the type of event that we want to spend a lot of resources on and monitor with other telescopes, and B, figure out when to start that like high frequency monitoring, because once we start that monitoring, we really want to bang at it, every night for, potentially a few weeks, and that's expensive. If we want to actually point the Webb or Chandra or this stuff, it's a super expensive thing. We think we can probably tell that it's the thing a month out or so. It really depends on the system. So some of them do take some months to rise. And so we can start watching and maybe take new extra observations to really figure out if this is the right thing. The trick is if we do this, and if we pull the trigger on all of our, what we call our target of opportunity observations, and it doesn't happen, we're not so sure that the telescopes will let us try again. So we're motivated to get it right.
So you kind of need to practice with less powerful telescopes, easier to get time on until you feel like you've nailed the timing. I mean, when I think about something very similar, I think about, say, gravitational microlensing as a way of detecting exoplanets, and that's a very well-worn field at this point. And those risings in brightness is very well known at this point, where they can detect the beginnings of a gravitational lensing transit. They send out to a vast network of even amateur astronomers who then will point their telescopes. They'll capture the moment where the lensing happens, detect exoplanets. It's amazing how well that field has been established. And so it sounds like we need to understand better how all of these bits and pieces come and play together. Okay, so let's imagine it's a perfect world. Vera Rubin detects one of these events. You're already really good at this, and you're sure that this is the one. You get time on all of the world's telescopes. You know exactly when you need it, including Webb, whatever you want, and you make your observations. What are you hoping to see?
So there are a number of things we can learn. There's a lot of information packed into that little rise and that little dip and the fall again. Even just from visible light wavelengths, we could learn a lot. We can learn, for example, the size of the black hole shadow and the mass of the black hole. And we can get those sort of independently because we can also get the velocity of the material orbiting the black hole. And the reason we can get that is because some of that stuff is moving towards us, some of it's moving away from us. And so we get this relativistic shift in the brightness. So the stuff moving towards us gets brighter and away from us gets dimmer. And so we can measure velocities. Combining this with our understanding of black hole physics, we can get the spin of the black hole. Okay, so the size of the shadow and the mass and all of this stuff gives us the spin of the black hole. This is something that we've never been able to measure before. Essentially, we can guess at it, and we've tried to guess at it, but being able to get any meaningful measure of the spin of the black hole, and then how all of this stuff connects to the physics of the quasar around it. We've long thought that, for example, black hole spin could be connected to magnetic fields. Magnetic fields could be connected to the production of the jet that shoots, above and below the black hole. So the idea is that we'll be able to piece a lot of things together, and maybe we see weird things that just don't make sense at all. In which case, we have to rethink all the stuff we thought we knew.
Now, if I put a picture, we're all familiar with M87's image from the Event Horizon Telescope. We're familiar with Sag A Star, the one in the heart of the Milky Way. If I then took a picture that was taken by the Event Horizon Telescope, if it could see a quasar, whatever the closest quasar is, I don't know, like 500 million light years away from us or something like that, and put it down in front of you, how do you think that it would look different if it had been shot by the Event Horizon Telescope? Would we see a lot of other interesting features in it?
I imagine it would be a lot brighter. So the two that would, Sagittarius A Star is not active, but M87 is active. So there is a radio jet. So clearly M87 is consuming some material, but it's not what we would call a full-blown quasar. It's it's certainly eating something. So but a full-blown quasar, the brightness near the center, like the rate at which material is pouring into that black hole, should be a lot higher. And so I guess if you could do a dynamic range right, then especially if you could get a larger field of view. So the black hole things we're seeing is really right close into the black hole. If we could see a little larger, then, and we could actually make out part of that accretion disk, that could be extremely informative. We're currently, when we do the physics of how matter falls into black holes, where we don't know much. There are some calculations done in the early 70s that assume some nice physics for how this accretion happens, and people have been essentially using that ever since, with some modifications and some playing around. But we really don't know. Turns out it would be good to know, because knowing how black holes grow, especially in the early universe, could solve some major mysteries about the interaction between black holes and galaxies.
Yeah, and it's funny. We're at this point now, and I wanted to kind of shift gears a bit now and just sort of chat about some of these. You are really fascinated with black holes, and like, who isn't? But we're making a lot of progress. We've got Webb now seeing the earliest known quasar, seeing supermassive black holes as they appeared less than 1 billion years after the Big Bang. Surprisingly massive. And then you're also seeing the images coming from the Event Horizon Telescope, not to mention all of the work that's being done by all of these other things that are seeing them in the X-rays, detecting, Chandra as well. How has your thinking on black holes in general changed over this last couple of years with Webb and some of these other telescopes on the job now?
Well, the EHT picture was remarkable because, although people who work on black holes do believe in black holes, I think the evidence is difficult to ignore. There is nothing else that could cause the quasar, and there's fairly good evidence in X-ray binaries, for example, that some of them have a neutron star that's cannibalizing their companion. but above a certain mass, things change a little bit, and it looks like things get swallowed by some dark spot. And of course, when we look for the huge gravitational mass at the center of our galaxy, the thing that's causing these stars to have these crazy orbits, there's nothing there, except for the occasional flash. So it's clear they exist. But seeing a picture, it really is funny. There's a real difference in knowing something's true, but knowing it's true or seeing that it's true. So that was pretty nice. As for the Webb, we've had this suspicion that things were a little off in the early universe. There was evidence that in the first billion, even half billion years after the Big Bang, or say 700 million years, that there were black holes that were a little too large. They didn't fit our understanding of how black holes grow. Okay, so assuming we understand accretion at all, which I have said we probably don't, but it took really straining our models to the limit and beyond, breaking our models to get black holes that big. There was one that was, I think, 10 billion times the mass of the sun, less than a billion years after the Big Bang. How does that happen? Because they have to start small. We assume they have to start small and then grow, but you just can't shove enough stuff into such a small region of space fast enough in order to do that by any mechanism that felt sensible. And so Webb has shed light on that. It's first of all, it's made the problem just more stark. So there's clearly something we don't understand. Those giant black holes are there, and I don't think it has yet resolved the issue, but it's found other unusual things about the early universe. Okay, galaxies being a little bit too well formed in some cases. So stars, what that indicates, perhaps galaxy formation itself is different to what we imagined. And we know the galaxy formation is connected to black hole formation. It's all tied together. It's all how things fall together under gravity. And so, perhaps we're getting more pieces of the puzzle that lets us finally connect it together in one story that grows us giant black holes and gets galaxies started much earlier than we thought.
I mean, there's kind of two major pathways for this, right? One is that you have clumps of gas collapse down, you get a star, the star explodes, you get a black hole finds another black hole, they merge together, then they find one that for a previous merger, and a few more doublings down the road, and you end up with 10 billion times the mass of the sun. The other pathway is that you have some mechanism that allows a gigantic cloud of gas to just collapse directly into a black hole of whatever mass is required. Both have their downsides. One is like, how do you get them to meet quickly enough to form that much of a black hole? And on the collapsing side, how do you get that much material in a small enough area that it can actually turn into a black hole? Do you feel like we're getting any kind of, up to this point, it's always felt 50-50. People are like, could be this, could be that. I don't know. Let's wait for Webb. Well, Webb's here. Where do you think this conversation is starting to go? Because I think you're right that you get a supermassive black hole forming early. That helps explain why you're getting a galaxy that looks a lot more mature early on in the universe. Where do you think we are on this?
I mean, so I don't think the answer's in, but Webb only just started. So some of the observations that we may hope for that will resolve this. So in the case of, if you want to make a giant black hole in the early universe, then it helps if whatever you're growing was already pretty big. Okay, so the so-called seeds of the supermassive black holes shouldn't be the sort of black holes that are commonly produced in our universe today, which might be 10 times the mass of the sun. Those things, it's almost impossible to grow big enough in time. But even 100 times the mass of the sun or more is quite tricky. But there are scenarios where you can have these just stupendously large early stars that could potentially leave behind a black hole after it after it explodes. And these things, like if you make a star that's 1,000 or 10,000 times the mass of the sun, then it's not going to live long. It's going to burn extremely hot, extremely fast, and leave behind a black hole quite quickly. And that black hole could, in different scenarios, could be 100 times, but could even be the whole mass of that star. The idea is that if that black hole gets big enough, so normally when a massive star dies, it explodes as a supernova, and it leaves behind a black hole core, and that black hole core is a small fraction of the total mass of that star. Maybe it's 20%. I can't remember the numbers, but there are scenarios whereby when normally a massive star will collapse, it'll sort of form a preliminary neutron star in the center. You'll get this rebound from the neutron star, sort of surfing this wave of neutrinos that flows out from the formation of the neutron star. And then if the neutron star is massive enough, it'll collapse into the black hole. But if everything is massive enough, then that initial collapse might not bounce back. The black hole that it forms might suck in everything. And there are also scenarios where the thing doesn't even form a star. It's just so massive. It just contracts and contracts and contracts. And so direct formation of black holes. So all of these things, the math checks out in the right conditions, but we don't know what the conditions are yet. And hopefully JWST has found evidence of what some of the earliest stars look like, but I think we're just still looking at those results and trying to come up with models that work and taking more observations. And I think over time we will get a better sense of the sort of stars that were forming in the early universe, whether it was even possible to form these ridiculously massive stars. Maybe we see them directly.
Yeah. And it's really tough because those first stars, those population 3 stars, are embedded within all of that initial gas and left over from the beginning of the universe. And so you can't see them directly until they have finished forming and cleared out all the material. And maybe you missed that party.
That is a problem. But, the fates of the first stars can also heavily influence how their galaxies then form and what the second generation of stars look like and all of this stuff. And that stuff Webb has, Webb can certainly see.
Yeah. I know Webb has seen the byproducts from those first stars, but hasn't necessarily been able to see those first stars directly. But then with like some of those more larger modern stars that we see today, I mean, there's a limit. You get to about 100 times the mass of the sun and the intense winds kick in and they blow away any more infalling material. The largest stars, when they detonate as supernova, don't leave a remnant behind in some cases. They just vaporize entirely. So that isn't a pathway to giant black holes. So it's really tricky. And yet, so how do you get a black hole with 10,000 times the mass of the sun if the winds kick in at 100 times the mass of the sun and blow away all that infalling material?
Well, I mean, I know some models show that you can, but the models depend on the assumptions in the models and the starting points. I mean, the key in the early universe is that the stars were very different, and the stars were different because the universe was a much cleaner place, let's say. All the generations of stars that happened since those first stars are element factories and have, let's say, polluted, luckily we're made of this stuff, but polluted the universe with the heavy elements of the periodic table due to the fusion that happens during the life of the star, but also even more so at their deaths. I'm talking about massive stars. But the very first stars formed from pure hydrogen and helium. And so in the first place, these things could be much bigger. And one reason is that the clouds that they collapse from collapse a lot more slowly. Okay, and so they can sort of ease into this gigantic star phase in the modern universe. When a cloud sort of reaches that critical point where it starts to collapse under its own gravity, it quickly fragments because it collapses a little bit too quickly. And it fragments because it collapses quickly because all of these heavy elements in the periodic table are very good at helping the star cool down. So the star generates heat as it collapses, or the cloud generates heat as it collapses. and that heat would normally stop the cloud from collapsing further. But if the cloud has heavy elements in it, then those heavy elements are able to reprocess the radiation of that heat, the infrared radiation of that heat, into different wavelengths that just exit the cloud. So they're able to basically act as these cooling agents. And so the star can keep collapsing and does so quite quickly, which ends up being a little chaotic. It can't sort of maintain a nice equilibrium shape. And so it breaks into pieces. And so you get smaller stars. Those pieces themselves become stars. In the early universe, where you just have hydrogen and helium, you have no way to enhance the cooling. The only way this thing can cool is by radiating from its outer surface, which is much, much slower. So these things do sort of settle down gently. Maybe they fragment, maybe not. But the possibility is that you then get this giant sphere, which, can be. I mean, these clouds that form stars in the modern universe can have millions of times the mass of the sun, and they end up making many, many stars. But imagine you took those millions of times the mass of the sun and just made a few stars out of it. So those could be gigantic. As for the winds, I'm afraid I don't have on the top of my head how the early stars avoid that particular scenario, except I know some smart people who think they do.
Yeah, no, and I've reported on this quite a bit, and also I wonder about the environment. Just like it was a denser place back then, and just a very different environment, and so maybe stars were force feeding material towards each other, and they
very
couldn't
much.
escape it.
Yeah, or even after the black hole forms, they could be force fed material, and there are ways to get around the limits that we think. In most scenarios, you can only grow a black hole so fast, because as the material falls in, things glow bright, and the radiation produced by that essentially the friction of material falling in then blasts more material, so there's like a choke point. But there are ways to trick the universe into shoving stuff down the black hole's throat.
Right. Yeah. Well, Meg, I hope you do get access to. I guess I have to say you don't need to hope to get access. Everybody's got access to all of the Vera Rubin data. It's going to be more about, are your algorithms up to the job?
Exactly.
Do you have the
Yeah.
database programming chops
we'll have
to
access.
find this stuff?
We're still kind of figuring out exactly, how quickly people get access to what types of data. The Rubin's going to observe so much data that it's part of it is a huge data problem. I mean, the knowing even how to store that much, but certainly you can't just have a website, you go in and get whatever you want. The data has to be processed, and so there are these, there are data products essentially, and we need like 5,000 spots on the sky to cut out that little thing for us every few days and run that through another pipeline to monitor these things. It's a challenge, but there's a lot of people working on it.
Yeah. Well, Matt, what are you obsessed with right now?
I think I just talked about it. I appreciate it. I'm newly enthused for the summer to spend a lot of time on this, but definitely pulling off this observation would be great. And in general, the Rubin, so my research team, and by the way, I need to shout out the first author of this paper, who was my graduate student, but is now Dr. Henry Best. He just graduated, just defended, and is starting his first postdoc. So he did all of the brilliant work there. But my research team in general is working on essentially preparing ourselves for this fire hose of data that we're about to get from Rubin, and particularly the gravitational lenses. And so I'm excited about the funky new techniques we're developing to try to just wrangle this data. There's just so much information that's going to be embedded in this stream of data, and it's so fun finding, just new ways to get what seemed ungettable from that data. A lot of it ends up being machine learning in this era. Our problem in particular lends itself to this approach. We can't use classical methods. It's so non-linear with all of these messy lenses and that we can't see. We can't use normal or classical methods. And so I'm quite excited about some of the machine learning approaches that we're developing to watch these lensed quasars.
I mean, I guess there is that main pipeline coming from Vera Rubin where they'll be identifying things that have sort of pre-selected. Oh, all these are new supernovas. Here's some interesting movements of asteroids and various interesting objects. But like the real gold is going to be in the full archive that you're going to have to dig through. But maybe if you can come up with a good algorithm, you can get promoted into that first one. Because time for you guys is very much in the essence. It's sort of too late if you look through
and we're
the
not.
archives.
So there are these alert brokers. So for certain types of object, there'll be alerts when they do certain things. Typically when they brighten or whatever. And a supernovae, for example, are a good one. But the alerts don't really work for our science case because that brightening, it happens over a bit too long a period of time, and there are subtleties that you need to disentangle to know that it's alert worthy. So we're in this middle case. We can't be woken up in the middle of night by the alarm that the supernova's gone off, turn on all the telescopes. Nor can we wait every year for the annual data release because that's too late. And so we need to, and we are crafting essentially a special pipeline that'll allow us to take the images of these lensed quasars. We don't need to get them the day that they're produced, but we need to get them that week, and then pump them through our custom pipelines really to do all the things. And so there are a lot of people working on this. There are some a couple of the LSST science collaborations are focused on this stuff for both understanding the lenses, understanding the quasars, but also, and I should add this because it's what more people are interested in. It's understanding dark energy. So one great hope for lensed quasars is to get an independent measurement of the expansion rate of the universe. And I would say, so our little case of wanting to map all of the black holes, we get a boost because some of the tools needed to do what we want to do is also helping a much larger collaboration try to measure the expansion history of the universe, and doing that, by the way, by measuring the different travel times of light along these different paths around the lens. And by doing that, they can get a distance measurement that is completely independent of all the other ways we measure distances to things in the universe. And by measuring distances, to various, distances or what we'd say call redshifts in the universe, we can basically track the expansion history in a way that hopefully could break the current big tension in what that expansion history was.
So if you do successfully map the event horizon of a quasar using a gravitational lens, will you do an episode of PBS Spacetime about it?
I might finally have to do an episode on my work. You should. I guess that's what it might take. I avoided it to this date. It felt a little biased. I don't know. I mean,
I don't think so. I think it's perfectly. You just say, "This is what I'm doing." If you think this
I could
is
interview
biased,
myself. Actually, that could be nice.
There you go. Exactly. Right. Well, now you've this is your rehearsal, and so I look forward to the episode.
Well, Maybe now it's been done. Maybe I can't beat this.
Oh, okay. Well, then there you go. All right. Thanks, Matt. Good luck with everything.
Appreciate it, Fraser.
I hope you enjoyed this interview with Matt O'Dowd. I'm going to give you some of my thoughts on the conversation, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bill, David Giltonen, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasnowski, Stephen Fowler-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. This research just strikes a bunch of the things that I'm really fascinated in, that we've got gravitational lensing as a way to be able to observe farther into the universe just using this natural gravitational lens than what we could do with our own telescopes. It's relying on Vera Rubin, which is going to be observing the entire night sky every couple of nights to find really interesting things like quasars that are brightening because we're about to get a glimpse at the actual event horizon. That sounds so great. And of course, we have all these questions about black holes, and a way to observe hundreds, maybe thousands eventually, of quasars at different depths into the universe can tell us a lot about the expansion of the universe, about dark energy, about the galaxies themselves, about the black holes themselves, and just all of these fundamental questions that we have just about the cosmos. And so I'm really glad. I'll let you know when Matt and his team find this lensing event and are able to report on directly imaging a quasar through a gravitational lens. But here's hoping. All right, we'll see you next time.